Hello everyone, sorry about that disaster. Started off in trouble for breaking a $600 microphone, so you know. Let's just see how we get on today. Okay, so what we're going to do when this eventually decides to wake up is we're going to continue with the rest of Lecture 8, where we're talking about Ito processes and Ito rule, so just carrying on from last week. And then we're going to move on to the kind of the business end, which is the Black-Scholes equation. We talked about that enough, so we'll finally get to see it. And some of you have probably already seen it many times if you're doing financial calculus and so forth. But we'll get to see it and look at some manipulations and how we use it. Again, just to say, I know there's like a lot of heavy maths in here, but really what I say to you is pretty much as deep as you need to go. And the only place that isn't the case, where you have to do a bit more in the assignment, I'll clearly point out to you, and if you've got questions or concerns about it, you can just come and talk to me. So that's the setup for today. Just a couple of announcements. One, assignment 2 is due today. I hope you all remember to finish that off. And then 2, assignment 3 will go up on on Blackboard this evening after class is finished. And you'll see the first 2 questions of assignment 3, and then next week I'll add the second 2 questions as well. So, sorry, no break, no rest in financial mathematics. So that was one thing. Second thing is on the exam scripts. There's one deferred exam tomorrow, and after that deferred exam, you'll be able to go and see Dwayne Min and pick up your exam script and have a look through it. I'll put an announcement on Blackboard telling you any conditions there are about looking at it and asking for remarking. But, you know, again, if you've got any concerns about that, just let me know. But you'll have to go to Dwayne Min to pick it up. I can't be bothered to bring the box all the way over here. That's the main reason. No, that's not true. And then the final thing is next week is going to be a guest lecture. It's from the manager of market risk at Suncorp. He's got lots and lots of experience, whole range of jobs. He's really good to talk to, depending on what you're wanting to do with your career. And he's also going to give kind of an interesting lecture that's quite different from a lot of the other stuff we've done this semester, but should be bringing it all together. So should be really good and interesting, and I hope that you can all make it and you get a lot out of it. So that's everything. Anyone got any concerns about any of that before I move on? Oh, yeah, and the last thing, 4 announcements. What about the last one? Which is, after class today, I'll be going through some mid-semester exam questions. If you're interested, you can come and talk to me. Okay? So, let's just, I forgot to plug this in. That's what I forgot to do. There we are. Okay. So I'll just skip through the lazy way. This will confuse all the people who are watching online. So Ito's rule. So we've talked about stochastic processes in continuous time. We did that at the start of, actually no, probably about halfway through last week. We talked about Ito integrals, and we got to the point where we were talking about this equation, the Ito process, and the different components of it at the end of last week. So that's slide 14. Then we played a little game where we kind of talked about the meaning of this drift and diffusion term. And so now that brings us to the final piece of the puzzle in terms of Ito processes, which is Ito rule. So the key result from last week is, shouldn't have gone off this so quickly, which is this Ito process equation here. And we spent a little bit of time arriving at this point. I guess the key things are, this is, anyone remember what big XT is? Yep, the price. Pretty much so this is the change in the price. What mu t is? Is that what to say? Drift. Oh, is it drift? Yeah, okay. So we've got drift, yep, drift dt, time. Sigma t was diffusion, great. And dwt, what was the w? That's right, yeah. So that's the underlying Brownian motion there. And we talked a little bit last week as well about how you can generally define mu and sigma in these terms. And I remember I had a few questions just about notation. So remembering that when we talk about big XT, and also we'll talk about big ST, as in being the stock price, and this generic price, really. These are random variables for a fixed time. Okay? As soon as we have a small x or a small s, these are used to denote independent variables. But don't worry about sigma and mu varying, because shortly they will not vary, and we don't have to think about that anymore. So the key thing is this guy up here, and you've all remembered what the components are from that. So what else can I say? Basically, this is going to depend on the entire history of W up to time t, and that same goes for the mu and the sigma t there. Yeah, and that's pretty much it. So that's our Ito's integral, and now we're going to move on to actual Ito's rule. Okay, so again, really important is that we are not concerned with the detailed maths behind this, and you are not going to be tested on this specifically. What you're going to be tested on is the application of this when we start talking about black skulls. So the next few slides are setting you up to understand how this all comes together. So don't worry about the actual derivation of it as such. I think you cover that in financial calculus, but you don't need to know that here. So just to make that totally clear. Okay. So to start with, let me switch this on. Which one am I? Right. Okay. So to start with, some key things to set the scene. So when we're talking about Ito's rule, we're talking about dt is a very small time period. Okay. So that's really important. So when we're talking about change in time, and we talk about t as t and moving towards t plus this small, very small time period. So this will be your change in time. Okay, and similarly, if we want to talk about change in price, x, due to some change in t, we talk about xt plus dt, and we say that this is equal to the original price plus some change in price. Okay, so we can also move on and talk about a change in some function of x due to the change in x. In which case, whatever our function of xt is, okay, and that equals so what we're moving towards, or what we're interested in, is what this little bit over here actually means. So far we've defined our change in time and our change in price, and now we're talking about the change here, where our function of xt is some Ito process. So we've got f of x, so now defining df of xt. Okay, and here we're going to subtract function of xt, where this is from, if I call this one up here 1, and this one down here 2. So this is coming about from 2. Okay. And then this is t plus dxt minus, again, the function of xt. And this is from 1. Okay. So what we're going to do is, now we've got to this final result down here. Is we can return to thinking about what's on this slide. So what we've got is our Ito process involving the price with the dynamics. dxt is mu dt plus sigma t dwt. What this says, dynamics of xt, dynamics meaning the movement of that price through time. Okay? And in this case, we're representing it using the Brownian motion that we're familiar with and the change in time, drift, and diffusion. And we say that f is a real valued function. Okay? And we want to know what are the dynamics of this function of xt. So as an example, if we take xt, some underlying asset, f of xt is the value of a derivative asset. If we know the dynamics of xt, for example, some of the many things we've done so far are binomial model for it. We've done stochastic process. We've looked at continuous time. We've looked at discrete time intervals. So lots and lots of options for describing the dynamics of xt. But if we know whatever the dynamics of xt are, we want to learn the dynamics of the function of xt and t. And comes back to what I said right early on when we talked about options. And I said, at this stage, all we know is a qualitative representation of an option price. Because we've made no assumption about the underlying, the dynamics of the underlying, we can't quantify what that option price actually is. So that's where all this is coming from. And if we go back to Ito's rule, okay, we've got a sufficiently smooth function, then some function of xt is an Ito process, and we land at this equation here. Okay? And that equation we're obtaining by applying a second-order Taylor expansion to this over here. We're only going to keep the first two terms, right? And we also need to think about or remember a few little rules. And these rules will come up again and again in various different forms, but the overall message is apply Taylor expansion. Okay. Keep first two terms. And then only keep dt terms. As soon as we've got dt to the k, where k is greater than 1, these are negligible. I can never spell negligible when I'm trying to write negligible. I think that's right. These are negligible. And this all comes back to what I said right at the beginning, which is dt is a very small time period. Okay? So we're only going to keep dt terms, not anything where dt is raised to the power of something. So this means, conveniently, that we can get rid of certain terms. So we can clearly get rid of dt squared. Okay? We can get rid of dw by dt. And we also know that dw squared is the same as dt, so we will retain this term. And this implies that in the end, probably need to start a new sheet of paper, that in the end, dx squared is this equation that we're all familiar with, okay, which is going to equal okay, which is so that's kind of a bit of a messy slide because we've covered a lot of things there and everything is a bit kind of juggled together. The next slide I'm hoping will add a bit more clarity to this, and if not, we can come back and revisit this slide. But essentially, this is what we've arrived at. We're looking at an Ito process for the price, okay, the price of the underlying, and we've used Ito's rule to get this df of xt. And we're talking about evaluating the partials of f at whatever x is at a point in time. And we're obtaining dxt squared by some multiplication rules. And we're getting rid of things because we're saying that dt is very, very small. So, as you've seen, and I just mentioned, it's just a second-order Taylor expansion. Okay? So the idea, if you were to go about proving this, which you don't have to do, but just as the idea of what you're going to do, you've got your second-order Taylor expansion here. What you want to remember is that the rules of stochastic calculus are just a bit different. It's the easiest kind of introduction to it. So second-order terms are no longer necessarily negligible. So although we can drop out dt squared, because it's much less than dt, and we can drop out, as I said on the previous slide, dt dwt, because this is still dt to some power, we can't drop out dwt squared because that's dt. So when we're talking about the Taylor expansion, there are some terms that will remain. This is just telling you really what you would know if you were using ordinary calculus, okay? But as dxt squared has terms involving dwt, which behaves like dt to the half, you cannot get rid of it. How's everyone feeling about this so far? Bit lost? Yes, yeah.
So why does dwt behave like dt to the half?
Okay, not for this course, but good question. good question, not for this course. But that's, yeah, these are the kind of, the bit, you know, below where we want to go. We just want to know that that's what happens, and that's why we can't ignore it. But yeah, good question. You doing financial calculus? Dwayne told me I should sell it to you if you're not doing it. So there goes the sales pitch. You'll learn all about this. Okay, so far we're kind of getting a bit of a picture of what's going on. Now, the next little step to add in is a sort of an example of Ito's rule, and this is going to lead us slowly towards where we want to get to, which is Black-Scholes. So now we've got the rules, the basic rules established. Now we just need to step through and try and piece the puzzle together so that we can get to Black-Scholes and know what we're doing. So the first thing to do is, I'm starting a new sheet here so that we can put this at the top. So I'm just going to put at the top here what we've seen of Ito's rules so far. Okay, so now we've got Ito's rule here, and we've decided there are certain terms we can and can't drop. The second important thing to write up is a comment about geometric Brownian motion. So as an example, we've already seen from the previous slide, got mu t dt plus sigma t dwt equals dxt. Okay. So now what we're going to do is we're going to take an example and talk about geometric Brownian motion. Now, geometric Brownian motion is very important, as you may have anticipated. This is what Black-Scholes assumes the dynamics are of the stock prices. Okay. Does anyone know much about geometric Brownian motion as compared to Brownian motion? Say again? So, sort of. And if we think about it just more like basically, we can talk about what some of the issues are with Brownian motion as it is for stock prices. So geometric Brownian motion kind of helps us get rid of a few of those steps. And, sorry, a few of those issues. So geometric Brownian motion is often, I guess that do you know what a return is for a stock? Anyone? The return of a stock? Yeah, that's pretty much right. So you're talking, rather than talking about the stock price as a kind of a single quantity, what you want to do is relate the stock price to changes over time. So often when you talk about stocks, you talk about the return from the stock rather than the stock price itself. So geometric Brownian motion is based on returns rather than pure stock prices. So that's one way. And this helps us get around the fact that actually stock prices could be negative if we applied pure Brownian motion. So that's one step that we take. I won't say too much else about that at the moment. I do think there were a couple of things I wanted to say. Don't want to get distracted. I am getting distracted already. Okay, so let's just leave it at that at the moment. So we're assuming, we're introducing geometric Brownian motion because Scholes assumes this for the dynamics of the stock prices. Okay, and so in our example, we're going to take dst is mu st dt plus sigma st dwt. Okay, so important points so far. One, rather than having mu as some function of time and varying, we've now got constant and constant, which makes life easier for us. And I'll come back to sigma being constant when we talk about Scholes, but just remember that's really important and something that everyone complains about when using Scholes in reality. We assume that ST exists and is positive. Okay? So now we want to know what are the dynamics of log ST. And the first time we're introducing log is because we're talking about geometric Brownian motion. And you'll see log again and again in the context of log returns of stock prices, which we'll define a little bit down the line. Okay, so what we need is function of S, okay, is log S. So we're assuming that this is how the stock prices behave. Then we've got F dash S is 1 over S, and F double dash S is, of course, minus 1 over S squared. Okay? So then we're going to use that. So using that this is what we're interested in, we get d log of ST, that describes the dynamics of our stock price movement, equals 1 over ST dST, and that's coming from this up here, okay, and 1/2 minus 1 over ST squared dST squared, coming from up here. Okay, so all we're saying is that this up here is our new kind of assumption, and what we've seen so far is that if we're describing the change in the dynamics of the stock of the price of the underlying, we use this equation here. So now, if the dynamics of my stock prices are governed by geometric Brownian motion, or up here, then I need to get my derivatives, so I can put them into this equation up here. Okay, and then I can substitute them in and get this slightly messy expression. Now, to simplify this down, well, actually, we're not going to simplify it down touch yet, but just to make this look even worse to start with. Okay, so dST, we know, is this guy up here. So we're going to substitute in dst down here. So we've got mu st dt plus sigma st dwt. Okay. And the other term, sorry, still incapable of writing on one line, is minus 1/2 1 over st squared. And again, we've got our friend dst squared here. And this, there's a little jump here, which I'll explain to you just now. But let me just put in, for now, sigma squared st squared dwt squared. I couldn't read my own writing. So, anyone remember where this comes from? Yep, that's right, yeah. So it's coming about because we made that assumption that the square of dt, or any power of dt, is going to be small and make it negligible. So it's disappearing. And can't read my writing, sorry. Yeah, does anyone want any further explanation on this, or do you want me to? Okay, great. Yeah. Yeah, are you okay, Cherish? Speak. You would like some more? Okay. Okay, well, if the step is in any way confusing, I can go through it, but yeah. Anyway, so just arising from this, removing that dt squared term. But easy for me to show you, just shout out, okay? So we're dropping dt squared, and we end up with this at the end here. And then we're going to take another step and simplify even further and end up down here. So pretty much just by cancelling out this stock term, stock price term, then we end up with, and grouping the terms, we end up with mu minus here, sigma squared over 2 dt, because this is dt, remember? And that plus sigma dwt. Okay. So kind of putting it all together, we've assumed that the underlying asset price follows a geometric Brownian motion rather than just your pure Brownian motion. And then we've done a bit of manipulation, used Ito's rule to get the differential of log st as we spoke about. We're getting the log of the stock price now. It's just a little introduction. And we end up with this expression down here. Similar terms, just slightly different format. So this corresponds to the, as I said, the geometric Brownian motion of the underlying stock price. Now that's obviously not enough. So now we need to know what happens over time, not just at a single point in time. Okay, so we're just going to integrate between 0 and t. And I think you can satisfy yourselves where this bit comes from. And the only thing to note is that we've got our log of st is log, so st is log normally distributed, or the log of st is normally distributed. Now, we can obtain an explicit expression for st in terms of wt, and this is probably a result you'll commonly see in a textbook, for example, okay, because, and so I'll put it up here for your satisfaction. Okay. So this is all being put together to get to a term for the stock price in terms of Brownian motion, drift and diffusion coefficients, and S naught, where S naught is the initial stock price. Okay. So please just remember, this is information building up to something. Don't worry about it too much. and go through it a little bit more if you want to. Just let me know. Now, I thought that it probably wasn't complicated enough at this stage. So the bad news is just need to make it a tiny bit more complicated, but you'll see why when we get to black skulls. So just, to think about where we're going. Again, when I keep saying we're going to get to black skulls, I just want you to think about what black skulls is going to give you, right? Which is the price, ultimately, of a call option in terms of the underlying stock price, ST, and the time. So 2 variables. So you need to add a second variable into this mix. So we're going to not only have X or S, we're also going to have Y or T. And what we're really interested in is the special case where YT equals T. So I'm going to spend a little tiny bit of time on this because you're going to see it in a few slides' time in Lecture 9. But really, you only need to worry about the case where that second variable is time. Okay? So for black skulls, we are interested in the 2 variable case. Where second variable is time. Okay? Now, if we have 2 Ito processes, say, okay, let's say one is dxt is mu1 dt, and the second one is dxt is mu2 dt plus sigma 2 dt. dwt, that should be, of course. Okay, these are going to be 2 Ito processes. And these would be used, I'll just flick one slide forward and then I'll come back. So when here we're talking about 2 Ito processes, xt and yt, this is what we are kind of meaning, is that you have 2 processes where you've got a different mu and sigma. Okay, so that's all that piece means. So we've got xt and yt are 2 Ito processes. Again, the function is sufficiently smooth. Then whatever the function of xt and yt is also an Ito process. And we have this long old equation here with the same multiplication rules as before. Now, as I said, the key thing we want is the special case, okay? So I'm going to write out this big old equation, and then we can whittle it down to obtain what we ultimately need, which is this special case. So df of xt and yt, where these are just 2 Ito processes, they've got partial times dxt plus partial dyt, and then the slightly more complicated bits. Yes? Yeah, so you could say that, so you can say that this is dyt and this is dxt. So just to demonstrate what I mean when I say 2 Ito processes, but yeah, just separate, same form, but just different mu's and sigmas, if that makes sense. Okay, so you've got dxt squared, nearly there, 1/2 d2f by dy squared, dyt squared, plus d2f dx dy dxt dyt. Okay, just put some brackets in there. Right, so what we want to know, we've got the same multiplication rules as before. So the really sort of important thing is we're going to drop all dt to the k, okay, which is good news. So we're going to keep this and this, but Yep, no, and we've got to keep this one. But this one we can get rid of, okay, because y here, don't forget, is t. So we've got x, y, x, we've got dt here, so this is dt squared, so we can get rid of this. And we can also get rid of this, okay, because for this one, this is our dt squared term, and this one is dt times terms involving dt and dwt. Okay, so again, that one drops out. So we've managed to get rid of these two terms, leaving us with this up here. So if we're saying I've got my special case where yt is equal to t and dyt is equal to dt, then I can end up with df of xt and t is df dt t plus df dx dxt, so this one, and then finally d2f by dx squared and dxt squared. Okay, so this, write this on a separate piece of paper, commit this to memory, because we're going to use it shortly, and this is really important. And the only difference is sometimes we'll say that xt is called st instead. But that's really the key result. So just by, okay, we've introduced a lot more complexity, but as I said, we have to for black skulls, so that's why all that comes in. So added these extra terms, 2 Ito processes now, one for the price, the underlying, and one for the time. Same multiplication rules. Same multiplication rules, so we drop out all dt to the power k. And this is also an important little point. X and y, we're saying, rely on the same Brownian motion. We're not changing that, so there's no difference between those two Brownian motions, which is why we can do this. When we allow multiple Brownian motions, if we do that, then we need an extra rule. Okay, in this special case, where yt is t, we can drop out a few terms. Anyone got any questions on this? Yes?
So what meaning of the second variable is time?
Yes.
Or is that like time is not variable in like a first Ito rule? Like not like is time is not variable like that?
So what we're saying here is not just that, so you're right, time is obviously a variable, but we're saying that time is now an Ito process. So it's not just a variable, it's now special. So it's an Ito process, and we have these two processes, both depending on the underlying Brownian motion. So that's where it's coming from. Kind of makes sense?
Like an xt and yt are like, what are they? Are they like asset prices?
No, they're not asset prices. As I said, they're just two. Was it dropped off the screen? No, so they're just two separate Ito processes, okay? XT, I've been talking about XT because it is going to be an asset price. So that's why I've kept kind of referring to it as a price, just to set you up for that. So that is an asset price, but this YT could be anything. It's just a second Ito process. So that's where it's coming from. So you've got two Ito processes.
You say it could be anything. What is the example?
So an example is, if you wanted them to be, you could have two different asset prices, both following Ito process. It could be two asset prices, but when you do black skulls, it's not going to be two asset prices. It's going to be an asset price, and it's going to be time. Okay? Any other questions? Yes?
Like when you did the cancellation, did this only applies when y is equal to t?
Yes.
In the other case, then you don't have that double
Yeah.
t situation.
Exactly. So I helpfully wrote that in a really small font just here. So you couldn't see it. So yeah, so in a really small font here, I'm doing this cancellation because I'm saying that that second variable is t.
And so, what is y of xt and yt? What is that?
In-
Just any function that is dependent on
So yt and xt?
no, f
Okay. Yeah, okay.
But what is f of x?
Yeah, so any function.
Any
Yeah, any function that's sufficiently smooth that meets the certain requirements. But for the purpose of this argument, any function. And we need to have a function, because when we come to Black-Scholes, it's a function of two things. Well, it's not just a function of two things, but when you derive it, you're looking at it being a function of stock and time, stock price and time. Yes? That's right, yeah, yeah, yeah.
So like YT could be like interest rate.
Yeah, but it's not. Just don't think about it. Don't overcomplicate things. Just have it. Just having y as t is all you need to know for now. Okay. Anything else? Important point. This. So yes.
Why we don't replace the dxt square with the object of to drop out some other.
Yeah. So I mean, we're gonna take this a bit further, but this is just as far as we need to go for now. But yeah, we're going to manipulate it in all sorts of different ways. But yeah, you'll be substituting things in and messing around and yeah. But okay. Really, any more questions? We're all vaguely happy with what we've seen, I'm guessing. Know where we're going. Okay. Last bit of hard work on this before we get to Black-Scholes. So we've got xt and yt as the Ito processes. Now, what we're doing here, I'm hoping will kind of make some of these questions make a bit more sense. But we're talking about the dynamics of zt as being xt times yt. So we're just making these two processes. We're putting them into this new function zt. Okay? So let the function of xy be x times y. Yes?
just that last one, why does that cancellation work? So dyt is now going to be dt, but
Yep.
then dxt, only one of the terms has a dt in it.
So dxt here has some terms involving dwt in it.
Oh.
Yeah. Yep, that's good. Good question. Okay. So much excitement about that slide. Okay, as I said, don't worry about it too much, but just I think we've got the required level of understanding now. So we're going to say now that we've got some function of xy, okay, which is going to be x times y, because we're now going to talk about the dynamics of zt is xt times yt. Okay, so we're going to say that partial df by dx is y, partial df by dy is x, partial df by dx squared equal to this, which equals 0, okay, and then finally d2f by dx dy is 1. Now, by Ito's rule, which I'm sure you're all bored of already, okay, where Ito's rule is this horrible-looking long equation. What we're going to arrive at, I'm not going to write the whole thing out, is dzt is yt dxt plus xt dyt plus dxt dyt. Right. Now, the key point, the intuition, if you will, is this term here, dx dy. If we were doing ordinary calculus, we would drop this if x and y are differentiable in t. Okay? We have to keep this if x and y are Ito processes. And that is because if it's dt times dt, then it's much less than dt. But as soon as we have dw, it is dt. Okay, so just the distinction, the final point between ordinary calculus and Ito calculus is this removal of that term, dt to the power k, but keeping any term that involves, say, dw squared. Okay, so I know that was a bit of a struggle, but I'm hoping that it'll all come together. Again, if you do financial calculus, you get into this in a lot more depth. But I've got a book as well that you can have a look at if you want to satisfy yourself on any of the derivation points. But yeah, just remember what you need to know for this, which is where it's taking us, which is Black-Scholes. Okay. So I'm just going to switch over lectures. Okay. So this is the exciting bit, the bit that you should have all been looking forward to, Lecture 9, Black-Scholes, okay? And I'm being funny, but it is kind of, it's the exciting result for you because it's just what you will always see as you move through your financial mathematics journey. And, you know, it's also the most common way to price options. And it's like it's a kind of the fundamental of financial mathematics. And Black-Scholes is super interesting. If you don't know about Black and Scholes, there was also Merton and Fisher. I always think it's sad when lots of people come up with a theory and then only 2 people get their name to it. But anyway, there were 4 of them. It was like an absolutely kind of cornerstone piece of work. They won the Nobel Prize for Economics, and it's still like absolutely widely used today. And I think the key thing about Black-Scholes is as soon as you go into any finance job where you're calculating options, somebody will say to you, oh, Black-Scholes is meaningless because volatility is constant. Okay, it's not, absolutely not meaningless because it's still used. And, you know, the assumptions that we make, like I said, when I was talking about sigma being constant, that's what I mean, volatility is constant. And these assumptions are kind of accepted as failings of the Black-Scholes equation, but it's still, you know, incredibly important. And we're just really scratching the surface. In this course, we'll just be, you know, we've kind of slowly built our way up to it. And then even in the end, when we get the solution to the Black-Scholes PD, it won't be very satisfying to anyone who's really into the maths, and you have to go to more courses and learn more about it to really get to grips with what this means. And I'll show you at the end the kind of the link between the different courses, as far as I know and from what Dwayman has told me. But it should give you a big picture of where you are. Anyway, so Black-Scholes. Now, what we're going to go through, first of all, is an intuitive derivation. It's not mathematically correct. I'll show you why that is. But it gives you the correct PDE, ultimately, which is what you want to start with. And then what we'll do is we will actually do more of a rigorous proof, and we will do that by constructing a replicating portfolio. So everything that we've talked about all this time, your arbitrage, replication, super-replication, sub-replication, filtration, all of these ideas are now all being kind of joined together to give you Black-Scholes. Now, the really mathematically correct derivation of Black-Scholes requires an absolutely extensive use of Ito calculus, and was way beyond what we've done in this course. So you'll have that to look forward to as you go forward. But anyway, before we go into all the maths again, I just thought I'd tell you what the Black-Scholes equation is, because it's easy to just get lost in the maths and oh, we're building up to this thing and we don't really know what it does. So basically, the Black-Scholes equation is a partial differential equation that governs the price evolution of an option. Now, usually that is a European call or a European put, the simplest type of option. And then you can develop into American options, but we're not going to go anywhere near that. I guess the main kind of financial insight is that you can perfectly hedge any option by buying and selling the right quantities of the underlying, and that's what Black Scholes is giving you. So as we've talked about, you know, we've got A shares and B bank accounts or bonds. This is all the same, exactly the same concepts. Now, if you can hedge by holding exactly the right number of shares and bank accounts, then that means there can only be one price for the option. So that's just something to keep in mind. But yeah, so that's basically where we're going today. So the goal really for today is finding the price of a European model under Black Scholes by the method of replication. Yeah, and as I said, the rigorous definition is beyond the scope. Oops, not sure if it was... Oh, I don't know how I did that. It's clever. Yeah, so I'm not sure there's anything else particularly I wanted to say. Sorry, just pressed the wrong button there. Okay. Right. So I'll write these on the visualizer. You've seen them enough times, but just still notation and more notation. So we're going to start with our old friend, if you will, arbitrage. And also, as I said, mention a few of these other concepts that we've met along the way. So first things first, we've got our fancy F, meaning filtration. Okay. And we've got some Ito process describing the price of an underlying asset. Okay, and this is a filtration adapted Ito process, i.e. any information from the market is going into this process to determine the price at whatever time period we are interested in. So we've got this, which is effectively our price and following the Ito process. Now, portfolio, big theta T, as in the number of assets that we're holding, of all the different types of assets, okay, or the quantity of assets held. Okay, so quantity of assets. Okay, where assets are going from 1 up to n. Now, the next thing, self-financing. Okay, we talked about this last week, not in a great deal of detail, but I guess the key things are the value of the portfolio is number of assets times the price of those assets. So I'll just put value here. Okay, and this satisfies this equation and equivalently the integral there. But for self-financing, if you just, as a little aside, remember, to start with, we talked about static portfolios, okay, where VT was theta xt, okay, and this was, I think, back in, I can't remember when we first introduced those, but anyway, so that's static portfolios, probably in the first or second lecture on these things. So self-financing, and this was in lecture 7, I've written it down, 7.818 for the definition. And that's where we've got theta t, is it t minus 1 xt equals theta t xt. If I've got that wrong, let me know. Anyway, and basically this means that change in value fully attributable, I'm pretty sure I spelled that wrong, to any gains and losses in asset price, okay? So just as a little refresher on what we mean when we're talking about self-financing. And self-financing and static portfolios, we talked about the relationship and special cases. Okay, so final point here, and again, the basis for everything that we do. Arbitrage is some self-financing strategy such that type 1 arbitrage definition, type 2 arbitrage definition, okay? So hopefully we're remembering back to the first time we saw arbitrage and defined them in these terms. But this guy up here is type 1, and this one is type 2. And you remember, we worry about type 1 mainly and not too much about type 2. Okay. So now we've refreshed on our various bits of notation, and we're going to talk about, and remembered what arbitrage is. Now we need to talk about replication. So, key things about replication. The definition. So it's a trading strategy, represented by big theta, that replicates a time t payoff yt if it is self-financing, and its value vt is yt with probability 1. Okay? So, replication. Whenever we talked about replicating an option, we were always concerned about replicating the option at maturity, and then working backwards using law of one price to say that at any time, the no arbitrage price of the asset, paying yt, has to be the value of the replicating portfolio, okay? So we used maturity price and worked backwards to time 0, and then said, okay, now we know time 0 price from our replication argument. Now, the long think about hedging here. Hedging is any strategy, remember, to reduce risk and ideally entirely remove it. So when you're hedging, you're trying to replicate the payoff, okay, whatever the payoff is, or a portion of the payoff if you're wanting to get rid of a certain piece of risk. But for now, just let's think about it in terms of you are trying to replicate a payoff, okay, and remove the risk. Now, this usually means getting the negative of the payoff. And if you hedge a position, what we've talked about a lot is short positions and long positions. So you could take a long position and a short position, and they balance each other out. And when we've talked about options, if you're short one option, you would then try and replicate the position by being long one option, effectively. And that would mean holding shares or bank accounts, whatever underlying is, to try and match that in the negative sense. We've also, don't forget, talked about super and sub-replication. If you've tried to bash your way through tutorial 9, part of that question, one of the first questions, is about super and sub-replication and what that gives you in terms of your ultimate portfolio. So that's important to kind of remember, this super and sub-replication argument. It's also very powerful. So that's replication. Now, armed with these two things, arbitrage and replication, and kind of try and bring everything together, we can now proceed with the actual derivation. I'm just conscious of time. Right, so what I'm going to do is I'm going to take you through the very first stages and show you the plan of what we're going to do. Then we'll have a little break, and then we'll come back and actually go through the different stages. So we need to be fresh for the exciting part of the lecture. No laughs at all, nothing, just sadness from all the maths. Okay, so we're going to now use what we've seen in the previous slides, where I've been talking about geometric Brownian motion and Brownian motion also. And I'm just going to talk a little bit more about geometric Brownian motion as compared with Brownian motion. So Brownian motion is like our natural starting point. That's where we started at the beginning of lecture 8. And as I kind of alluded to, there are a few problems with Brownian motion as a model for a stock price. Okay, number one, it can be negative, which is really no good for us at all. So you can actually scale Brownian motion with the drift term, but it being negative is a bit of a problem. Okay? Now then what I talked about with returns, okay? Basically, if we represent the change in stock price using a Brownian motion, then each little change in stock price between 2 times is independent of filtration. So it's independent of additional information coming into the market. I.e., if you move $10, it doesn't matter whether you're at $20 price or $200 price, the move of $10 would be equally likely, which doesn't make a lot of sense when you think about the actual market. And if you held some stocks that were worth $200, you would expect them to move $10 much more easily than if you held a stock that was worth $20, proportional to the price, okay? So that's where that's coming from. So then, when we introduce geometric Brownian motion, we solve a few issues. Okay, drift and diffusion now become proportional to the stock price, and the stock price stays positive, which is great. Okay, and then here we introduce this concept of log return. So like we were talking about, basically this is a way of representing the change in stock price, and the logarithm of that is independent of filtration. Okay, so a 10% move is going to be equally likely whether we're at 20 or 200, which makes a lot more sense. Okay, so this is why we introduced the idea of geometric Brownian motion. Yeah, okay, there wasn't anything else, just wanted to double check. So, putting up a few more key things. Now, these two are really important, and we're going to return to them. Remember I said to you to put a box around one thing? Put a box around this as well, because I'll reference it and you won't kind of expect it to be coming up. So make sure you've got it somewhere handy. Okay? So in continuous time, we're just going to have our 2 basic assets again. There are more than 2 assets out there. You wouldn't have guessed so far, but you've got your bank account and your non-dividend paying stock. Now, this one up here, you've seen before, okay, and this is important, so put a big square around it. With your bank account, okay, we're familiar with a unit has a price, okay, e to the RT. And also, we introduced this, but kind of in passing, we said, this rule applies. I think it was in lecture 6 even. But what we need to know is the dynamics, how it moves, follows this equation. Okay, where, as always with a bank account, we say that we start off by putting $1 in the bank account. So this here is very important. Okay. And the second thing, a second asset, so this is like asset 1 and asset 2, okay, is our non-dividend paying stock, okay, with price S. Now, this is familiar to you, I'm sure, from what we've just been doing. Oh, I've written the wrong thing there. Okay, so we've got our, let me show it up here, it's much clearer. So we've got our Brownian motion, got our stock price and our sigma, we've got our mu and our stock price and our time term, and this is the geometric Brownian motion dynamics, okay? And when we just talked on this slide, we said that the drift and the diffusion are proportional to S, i.e. in here we've introduced the share price into our drift and our diffusion terms. Now importantly, our volatility, sigma is greater than 0, and W is a Brownian motion under the physical probabilities. So with Black-Scholes, what we're trying to do is find the price of a call option which pays, I'll put a little box around this as well, it's also important. Okay, which pays share price minus strike price, the positive value of that, at T. Okay? So this is what we're interested in. Now, as we go on, and we're going to talk about the intuitive derivation, just the plan in a minute. As we go through, just remember this equation, and remember that for a put, it would just be the other way around, okay? Because this equation here is going to be a condition as we go forward, and it's also directly related to all that stuff we did about payoff diagrams and, you know, trying to work out what upper and lower bounds of options are. So try and keep that all in the back of your mind with this one. Okay, so I'm just going to tell you what the intuitive derivation is, and then we can have a little break and then come back and actually go through it. So, okay, so this is going to be our first go. Okay, so we're going to price options using replication. I already mentioned that. We could be using the risk-neutral pricing. We're not going to do that. You'll do that in 4091. So we don't cover that in this course. That's also presented in quite a few textbooks. So if you do see that, don't worry about it. We're not going to do that here. Okay? Now, to do this, we're going to construct some risk-free portfolio, i.e. a hedged portfolio where we're replicating of some calls and some stocks. Okay, and risk-free here means that the DW term, the Brownian motion term, is going to be 0. Now, if it's self-financing, then it's going to grow at the risk-free interest rate, or there's going to be arbitrage of the portfolio as compared with the bank account. So this is the key difference between, or it's one of the differences between the two approaches we're going to have. This first try, we're going to be replicating our bank account using a call and a stock. But as we go to the other definition, or the other derivation, we'll be replicating the call option using the bank account and the stock. So just keep that in mind. So self-financing, and then we're going to represent this call equation, the function, the expression for the call option using Ito's rule to do the partials. Then we're going to say it satisfies a PDE, and then we're going to solve the PDE to obtain a formula for C, okay? So what I'm going to do is I'm probably going to write this up and write the little numbers for the lectures next to it so that you have that handy if you want to refer to it as we go through. But yeah, so let's have a break, and then we'll get back to it. So if you can get back about 25 to, so 15 minutes. Okay, we'll get going again. So what I've done is I've written up over here what lecture slides correspond to these various bits, okay, at least in the first intuitive derivation bit, okay? And don't forget, we'll revisit some of these in a more rigorous way in the actual full derivation that we'll do just after intuitive. So basically, constructing a risk-free portfolio and self-financing is 9.10. Ito's rule on partials is 9.11, and PDE and solving the PDE is 9.12. So 9.12, 9.11, 9.10, 9.10, just so you can keep track, but you'll see as we go along. Okay, so this is what we're going to do now, hopefully. So first of all, we're going to construct our risk-free portfolio. Now, as I mentioned, we're constructing a risk-free portfolio, and we're basing this on a bank account. And we're saying we want a bank account in terms of some number of options, call options, and some number of stocks. So, keep it simple. We're going to have one option and minus 80 shares. Okay? And what we're going to do is we're going to actually choose 80 to cancel out the option risk, coming back to that whole idea of hedging or removing the risk. So the portfolio value, VT, is going to be whatever the call is, minus A times shares. So we've got value is call minus a number of shares. Okay, so we've got 80 shares. And then we've got one call option at the moment. Okay, now, why what we're doing is not strictly correct? So it says, so some authors assert that. So this means that if you see this proof in a textbook and it doesn't have this disclaimer, then, you know, they're not doing it correctly. So basically, sometimes you'll see this written. Okay, so where we're doing the change in the value of the portfolio is the change in the call option price minus A times the change in the stock price. But as we've just seen from Ito's rule, this is not correct. And actually, the derivative of AT-ST would include all of these terms. So it's not true to just say that it just equals this. I'll come back to that. Will I do that now? No. Okay. So I'll come back to that in a few slides' time. But that's why what we're doing is not strictly correct. So now you can feel really smart if you read a textbook and you know this and they don't. But I'm just joking. Okay. So we're going to now construct our risk-free portfolio. So now we've got in mind that what our portfolio value is. And I want you to also remember the first thing I said, draw a big box around, special case. Okay, where we have df(xt)t equals partial df(dt) dt plus partial df(dx) dxt plus 1 half d2f by dx squared dxt squared. Okay. So, keeping this in mind, what we can see is if in my portfolio, V, I have two things. I have calls and I have stocks. Then I'm going to introduce calls and stocks into this equation here. Okay? So, remembering our special case, we have the call option as I said to you, is some function of stocks and some function of stock price and time. Okay, and it's a smooth function. And this means by Ito, we can see that dVt, changing my portfolio value, okay, is going to be partial stock with respect to time plus partial of the call option with respect to time plus partial of the call option with respect to the stock price. Okay, so we've got here ST and T, because we have these here. Okay, and plus 1/2 d2c by ds squared dst squared. Okay, so just following on from that special case that we had here. And because of what we talked about, and I should have written this up, but I'll write it up now. So what we talked about here, not strictly correct, but we'll do for now, dVt equals dCt minus AT dSt. Okay. Because of that, we now have this additional little term out here. Okay, because we're saying that dVt is dCt, okay, which we've written out pretty much already. This is dCt. We've also got to get rid of this little bit here to give us dVt. Okay, that clear, hopefully? So we also need to, and I'll write this in a different color, minus AT dSt. Okay, so far so good. Just use what we've got so far, replicating our portfolio. No, not so far so good. No. Yeah. Yeah. Yep, so this is the portfolio. Yep, using this. Yeah. So now because we're talking, yeah.
Yeah, so with the first half, you're applying equal process, but with the second half, we just ignore the fact that it's not.
Yeah, so for the second half, we're pretending that we don't know that this is a mistake, and we're just saying that, okay, we think that it's this. So that's why it's not rigorous. But, you know, now we're all in the know, we can realize that and just, you know, move that to one side and progress, okay? So as long as you're roughly clear where this is coming from, and albeit with a mistake in it, that we know what this is. And that's why it's in blue on the slide, and I've written it in red as well. Okay, and we've got here where C, represents the call option, and its partial derivatives are all evaluated at STT. Okay? Now we're going to make these cancel out by cleverly choosing my number of shares. A equals dC by ds, STT. Okay? And, of course, cleverly, because I've chosen A to equal this, and this is going to go in here, then you can see that we can cancel certainly one term. And we can also make a little simplification, and we can arrive at dVt is dC by dt, this term, okay, plus 1/2 d2c by ds squared dst squared, okay? And remembering that because we've set A to be this, then we can knock out these two terms here. Now we can simplify this, or simplify if you will. Just got to remember one little thing, which is, and this is from wrote down what slide it was. 9.8 we have there. So we've got dst equals mu st dt plus sigma st dwt. Okay, we saw that many times. So then we can say dst by st is going to be mu dt plus sigma dwt. And of course, if we square this term here, okay, and knowing what we know about what happens to dt, as soon as we square this term, we get rid of mu dt, and we end up with sigma squared dt. So remembering that, we can move to this second little bit here, where we've now got sigma squared s squared instead of dst squared. Okay, so we're dropping down to dc dt plus 1/2 d2c ds squared sigma squared st squared dt. Okay, so that is our portfolio value, change in portfolio value, where we've assumed or chosen our number of shares AT to be the same as this term here, so these guys fall out, and you're left with a portfolio value of this. Now, on the other hand, remembering what I said, which is with the portfolio, what we're doing is we're using a number of calls and a number of stocks, in this case 1 call and AT stocks, to replicate a bank account or a risk-free portfolio. So the second part comes from this idea here. So what we're saying is dVt equals rVt dt. And if you remember, the other important thing I told you to draw a box around was this idea that dBt equals rBt dt. So instead of just having our bank account now, sorry, I was pointing the wrong way. So now, instead of worrying about our bank account, we're talking about our portfolio and this risk-free portfolio. So what we can do is we can use the same expression that we had for our bank account. So we've got our risk-free portfolio here, represented by this. And substituting in for Vt from, where have I put Vt? Have I put that up yet? C minus St, okay. So I should have done that. Yes, I have, yeah, of course. So Vt is Ct minus At St, and where I've made an assumption about At being dc by ds. So I can substitute that in here for Vt. So now I'm getting this is equal to R times C minus A stocks, which is, of course, dc by ds stocks, times stocks dt. Okay? And then all that remains, now I've got these two expressions for the portfolio, the change in portfolio value, is I'm going to compare the right-hand side. So I'm going to say, okay, I've got this guy up here from replication, and I've got this guy down here from assuming risk-free, and one of my terms has already dropped out, so I can obtain this equation at the bottom. So putting that together, we've got comparing right-hand side, we've got dc by dt plus, sorry, dc over ds st from over here. Okay. And dc by ds, sorry, I forgot the r, importantly. I don't know where to put it now. Put it here, maybe. Is that confusing? I'll put it here. It's even more confusing. Anyway, you know where we're going with this. It says T plus 1/2 d2c ds squared sigma squared st squared from here, okay, equals RC from here. Yes? Okay, so that's just from the principle that when we talked about the bank account. Let me go back for you. Here. So when we talked about the bank account and we talked about the dynamics here, we used this. But if we talk about the portfolio and we say that it's risk-free, we can make the same assumption. Yeah. Okay. So any more questions on that? We've compared the right-hand sides and we've arrived at this lovely-looking formula down the bottom here. No, all good? Okay. So got this great-looking formula, and the exciting news is we've actually got there pretty much already. So this is the Black-Scholes PDE. This up here is was our end goal. And okay, we haven't got there totally accurately. We've talked about that little issue where we've assumed that the derivative the derivative here, dATST, is this. But apart from that, we've managed to get to a PDE here. And it's got these conditions. So the key one that we'll see again and again is the terminal condition, which is that payoff function up here. Okay? Now, the solution is the Black-Scholes formula. And it's this bit of a mess at the bottom down here. But what we need to keep in mind is what we've done is we've done this work to get to this PDE, the Black-Scholes PDE. Okay? And then we can do some more work, as we'll see, in order to get the Black-Scholes formula down the bottom here. So we've kind of done the hard work already, which I hope you'll be pleased to know. Yes, Cherish, you look confused. Yeah, so this is your Black-Scholes PDE here, with a terminal condition and your other conditions here. And this is the Black-Scholes formula, the solution of that PDE. Yeah.
So S is the same as S.
S is the S here? So yeah, so that's your stock price. Okay? So you've got your stock price, your strike or exercise price, T time to maturity, R risk-free rate, sigma squared is your volatility. If you're eagle-eyed, you will notice that you actually don't have the expected return in there, that mu anymore, that's not in there. But otherwise, all of these terms you've seen before. Okay, and yes? C is still a function of S and T, yeah. Yes?
And the result S plus N, B1, the S is to the stock price?
Where are you looking, sorry?
In the formula, so
Down here?
Sn, is it S times N?
That's correct, yep.
It's to the stock price?
Yep, that's still the stock price, yep.
And N is a function?
So N is now, we'll come on to that, don't worry. We'll go through that in a minute. But yeah, so this is the thing that we've worked towards. So we've got our PDE. And when I said before, I wish I hadn't lost that sheet of paper. So basically what we've done is we've used Ito's rule on the partials, 9.11, and now we've found out that actually the solution here satisfies this PDE that we've spent that time trying to derive. So this is where we are, and we're going to solve that PDE to obtain C. Of course, we haven't solved it. I've just given you the solution. But for now, you would just imagine until a couple of slides' time, that you would then solve this PDE up here to arrive at this solution here. Okay, and we'll talk a little bit more through that solution just now. Okay. So we'll talk a bit more through that solution, and then we'll go on to the careful proof. Right. So is everyone happy about how we got to the PDE? Roughly speaking? Yeah, okay. So key thing, as I said, is the terminal condition, which is that payoff function, right? And we've got the PDE, which we just did using the replication argument and the risk-free portfolio. Now the solution, how we get to this, I will show you shortly. But the solution has got two key terms here, okay? And the term involving the normal distribution, n of x, is the CDF of the standard normal. And where in brackets for x we have d1 and d2. d1 and d2 are the positive and negative results of this equation down here. Okay? Now, we've got our stock price, and we've got something that looks a lot like a bond price on the right-hand side. So you can still almost relate it to what you kind of think of when you think of how we replicated those options to start with using the stock and the bond. So this here, you've got your stock, and just here, you've got almost your bond price. And that is S minus K is kind of coming in through here. So you can see why this would be your terminal condition, and you can kind of, I hope, start to link the two together. Now, as I said here, you've got your stock minus your exercise price, and that is the limit of the Black-Scholes equation as you tend towards maturity. And I'm going to skip ahead just a couple of slides to show you what I mean. Because if we plot the equations, and we've seen something similar to this before, we see that, here we go, red line, okay, is giving me, it's st minus k e to the minus rt. Don't worry about intrinsic value too much. We can see the option price, the black line, tends towards the red line. But we'll come back to that shortly. All right? So this is where we've been trying to get to all semester. This is kind of the conclusion. And it doesn't stop here. We're not really going to use this particularly. We're just going to kind of look at it and say, oh, doesn't it look complicated? And maybe you go home and put a few numbers into it and see what happens. But what we're going to do is we're going to work out how you actually get to CBS from this PDE. But this slide really contains the kind of the key results and what you've been working towards. So I'm surprised there's not more excitement about this. just terror. Okay. Great. So just back to what we were talking about before, which is the how not to do stochastic calculus. Okay, so this claim here that we made that you could just use ADST in place of the actual Ito's rule, what Ito's rule gives you. There are some justifications that are used to make that simplifying assumption. I would just suggest you just ignore them and just accept that you've done it the wrong way and you need to do it a different way if you want to get it right. Like things like shareholdings are instantaneously constant, it doesn't make any sense because otherwise you wouldn't even be able to replicate the portfolio. That's the other kind of point. So they're not instantaneously constant. AT is changing, and that's why you have to have Ito's calculus, because you're saying it's Brown in motion. And then the other one is that it's self-financing, which it isn't because you can't vary the shareholdings without providing outside funding, because you only have one option. Okay. Now, so the intuitive derivation is very useful because it got us to our end goal, but it's not an actual proof. So what we're going to do is just go through that proof carefully now. Okay. So the careful proof. And this is still not the real proof either, so as I said, you've got to do Dwayne-Min's class if you want that. Okay, so what we did before was we were replicating a bank account using an option, a call option, and a stock. Now we're going to replicate the option using a stock and a bank account. Okay, so we're just slightly switching things around. Same assets, stocks, bank accounts, options, but just slightly in a different order. Now, we know that CBS, as a function of stock price and time, is the Black-Scholes formula. Okay? And as we've seen that on the previous page. And what we're not assuming is that this is the options price. That's the conclusion of this exercise. So let's decide when we're replicating. Don't forget, kind of our first decision is how many of S and of B. So what we're going to do is we're going to say that the portfolio value, AT, ST plus BT, we're going to say that AT we're going to hold same as we did before. Okay, so this many shares. And we're going to hold this many, sorry, let me make that clearer, this many bank accounts. Okay, so then, assuming that we're going to hold this many shares and this many bank accounts, and that this is our portfolio value, also can say that the portfolio value is 80 shares plus, substituting in for BT, we get CBS STT minus A stocks, which happily equals i.e. the portfolio value, if we select this many shares and this many bank account units, the portfolio value is equal to the Black-Scholes formula. Okay. Now, in particular, the terminal value, which I talked about in the previous derivation, and when I say terminal value, by the way, I mean the value of the option at the time that it actually matures. Okay, that's what I mean by terminal value. So the terminal value is given by this here. So we have CBS, and that's the stock price at maturity, and time is stock price at maturity minus exercise price and the positive version of that. Okay. Now, the final piece of the puzzle is just saying, working out or confirming that it self-finances. Yes, yeah. Sorry. Okay, yeah, you can correct that, right. Yeah. Okay, so we've got our, yeah, as you say, sorry, that what I've written here, this small t is a capital T. Thank you. Okay, so we've got capital T here, time at, so this is the call value at maturity. Now, the next piece is we have to confirm that it self-finances. Okay, so we have change in portfolio value is going to be the change in this, because we've confirmed that here, VT is equal to this. So using this, we come down here. So we've got our change in portfolio value. Now we need to substitute a few old favorites in. So to start with, we're going to substitute in from 9.10. If we remember, this is what I'm going back to here, okay, just to let you know. So 9.10, 9.11. TVT, okay, so self-finances. So we've got the change in portfolio value is going to be dC by dt plus 1/2 d2c ds squared sigma squared st squared dt plus dcbs ds dst. And I'm hoping that I can really quickly find that so you're satisfied. Ds here. Okay, so this is coming from when we did this bit of work and we talked about the special case, and then we fiddled around and we set the number of shares, and what we obtained was this equation here, which looks a lot like here. Got our dc by dt term, we've got our d2s dst squared, where we, down here, did a bit of fiddling around and substituted in, okay, sigma squared and st squared. So we've got this here, the change in portfolio value. And then don't forget, we also, because we've introduced a number of shares, we need to add in our number of shares times dst, okay, because, of course, we have a portfolio that's not just bank accounts, it's also a certain number of stocks. So that's where that is coming from. Which one? Where? Here? Here? Yeah. Yeah. So what we're saying here is, if we compare these two equations, I should have just done it like this, really, shouldn't I? Okay. So we've got this one, we're fine, no problem here. This one we're also happy with, okay? Now, the thing that we're not happy with, or we're kind of concerned about, is what about this term here? Yeah? Is that what you're saying? And this
entire equation equals VT.
So this equals, so we had the right-hand side and the left-hand side here. So here we've got dVT, and this is our portfolio value, okay? But don't forget, in this case, we had made an assumption earlier, right, where we'd set the number of shares. AT is DC, DS, and we'd knocked out a term up here, okay? So that's where that came from. Yeah. And then we set them to be equivalent to each other.
Okay, so those two are
So if you, okay, so there's a couple of ways of thinking about this. So they do exist, right? But if you're setting up a risk-free portfolio, then you're not going to have an R term, any terms with R in, because there's no risk. So the risk-free rate would be 0, say. Okay? So you can think about it in that way. If I just complete this one, and then we'll come back to it if we need to. Okay, so just to finish this little piece off here, so we've got our equation here and our term for the number of shares. So now we're just going to do a substitution here, okay, and arrive at, lost track of what color pen I'm supposed to be using. Okay, so then we're going to substitute in Okay, and same thing again here. And what we end up with after using the fact that we know that this is 80, and this expression here is our BT term from just up here. So now what we've got is just switching this around, so saying A first, AT dST plus BT from up here times dBT. Okay, so we've got CBS satisfying the PDE by direct computation. So we can confirm that the portfolio replicates the option. So just to recap, we decided to hold A shares, B bank accounts. We talked about what the portfolio value is. Okay. Then we have looked at the terminal value, and we've talked about how it self-finances, because we can prove that dV by dVT equals dCBS, and we can go back and arrive at a term involving a number of stocks and a number of bank accounts. And then we can conclude, because of the law of one price, that at any time t is less than t, the unique price of the option equals the portfolio value. Okay? So I'm just going to move on, because I don't want to run out of time, but I will come back to this after the lecture, and we can go through it in detail if you want to, or if there's a little bit of time at the end, but just so I don't totally mess up my timing. Okay, so that's where that's coming from. As I said, I can run through this again and try and get all my papers in order so you can be satisfied where that appears from. So on this note, I think what we, I guess, have seen and have talked about a little bit in the past when we did payoff diagrams is the idea that the option price is bounded. And I think I drew a diagram for you when we were doing payoffs, and it would have had the stock price out here as a kind of as a diagonal line, and it would have had the same curved line for the option price. I don't think I talked about intrinsic value, but I definitely would have talked about this equation here as the lower bound of the option price. Okay, so this is option price up the y-axis, and along here is the stock price. And we have seen this before, and I'll scribble up a diagram in a minute. The key thing I wanted to note is about the intrinsic value. Okay, that's a specific definition, the intrinsic value of an option, and it's defined in the case of a call option by the stock price minus the strike price, the maximum of that and 0. So that's the intrinsic value of an option. If you remember way back when, just before the mid-semester break, I actually defined intrinsic value for you and told you about the difference between the intrinsic value of the option, its price, the intrinsic value of an option compared with the actual value of the option and the other factors that go into the option to make the real value of the option. So that's where that's coming from. But if you remember, I'll just scribble this up quickly, that what we talked about when we were doing all those payoff diagrams, we're talking about option price, stock price, we had an upper bound, which was the stock price, and we had the lower bound. And I said that the option price does this. Okay? Well, that's S naught. And we talked about the max of S minus KZ, and 0 is less than or equal to C is less than or equal to S. Okay? So what we're seeing here is not much different to what we plotted in a payoff diagram before we knew anything about the behavior of options. But now, the good thing is that you can now put in some numbers and satisfy yourself that this relationship that I kind of scribbled up, this line doesn't look very curved on this diagram, but this line here is curved, just in case you can't tell. Okay? So, and how you arrive ultimately at this curved line. So the payoff diagrams now, if you revisit them and you do want to plot some numbers, you should see that that kind of starts to make a bit more sense. Right. Okay. So this we're going to skip. The fundamental theorem holds in continuous time. You don't need to worry about a proof or anything like that, just so you know we haven't forgotten about that. Okay, so now the final, I guess, piece of the puzzle is the PDE. The solution to the PDE. So when I was talking all the way back here, and I was saying, oh, okay, you've got your PDE, and by the way, this is the solution. Obviously, a little bit more to it than that. You have to actually work out how you get to the solution. Now, this is one of those places where I'm going to tell you a certain amount, and then we'll get to one slide, and I'll say you're going to do this in assignment 3, but hopefully by that point you'll have enough information to be able to work through those steps yourself, and if you don't feel like you do, then just come and talk to me, and we'll go through it. But bear in mind that assignment question will come next week, so maybe better to have a little think through and come back to me next week if you feel like you just desperately can't do that. Okay. So, final piece here is the Black-Scholes PDE. So this is the the solution time, and this is the really getting to the ultimate result. So just completing the picture, I'm just going to write up again the Black-Scholes PDE with all of the things we're familiar with in. Okay, and I'm not going to worry about that, but I will write the terminal condition. Okay, so a few things to note before we get started. Number one, it's a backwards PDE. Like everything we've done with options, excuse me, we start at maturity at time t, or exercise, or whatever you want to call that time, out of big time t, and we want to obtain the option price at time 0. So like everything, the binomial models, all of that, we've always started out at t and we've worked backwards to 0. Okay, so no different here. Now what we're going to do is the way that we're going to solve the Black-Scholes PDE is reduce it to the heat equation, which has a fundamental solution. Now, this is going to be done via a change of variables, and I'll tell you what that change of variables is. And then you'll need to reverse the change of variables to pop out the answer of using the actual variables. So that's the plan, okay? So are any of you familiar with the heat equation, the diffusion equation? Yeah, you've seen it before? Great, excellent, okay. So you can tell me what I'm doing instead of me trying to get through this. Okay, so we've got the diffusion equation. Now, the PDE, as some of you may well be familiar with, and I really apologize, I'm just really bad at drawing various Greek letters, but hopefully it's clear enough. Okay, equals 0. Okay, so that's the PDE. And then, importantly, we have our initial condition. Okay. Yep, so it's the heat equation. Yeah. Oh, and in a minute, I'll just tell you about the different pieces of it. So this is the heat equation, or diffusion equation, whatever you're more familiar with calling it. Okay. And it has a solution, which I'll also write up, okay, which is U Z tau 1 divided by 2 by sigma squared tau minus infinity exponential Okay, so sorry, this is one I really can't draw. Okay, so we've got PDE, initial condition, and solution. Okay, so intuitively, don't laugh at my Greek letters. Okay, so intuitively, PDE, initial condition solution. So what's the PDE doing? We're describing the concentration, U, okay, at position Z and time tau of any substance, a dye, whatever, propagating in an infinite one-dimensional medium. The PDE comes from physical laws, and the rate of movement is proportional to the concentration gradient. So that's what this is saying. Not that that matters at all to us, because we're just going to use it however we want to solve something else anyway. But that's what it's doing. So when we get the solution, ultimately, we're saying that a 1-unit point mass of the substance, okay, which is initially located at, I never know whether this is zeta, but I'm just going to call it squiggle. So when I say squiggle, this is what I mean here, okay? Just to confuse you. So we've got a 1-unit point mass initially located here at squiggle, and it diffuses. So at time tau, it has a position Z, okay? And then this piece here, okay, is important. So that's the concentration. And if the initial concentration, some function here, then at each squiggle, then the concentration at position in Z and tau is going to be the total of all the contributions from every squiggle, i.e. we add in this little piece here. Okay? So this is from this piece of information here. So this is a very crash course in this PDE. Hopefully you've seen it before. If you haven't seen it before, then, and you're not satisfied with this very kind of rough and ready interpretation, then go and have a look at it. But we're going to use it, not worry about it too much. So don't lose any sleep if it's not massively, intuitively clear, the physical properties of it. Okay. So just a key little thing here about this piece of the equation, which I've also drawn a box around just up here. Okay, so this without the integral here. This is sometimes called the diffusion kernel or fundamental solution, and you'll notice that we've talked about diffusion before. When we've been talking about Brownian motion, we've had that diffusion term. So when we've got a normal, the normal here density, each of the particles is following a Brownian motion. So it's not totally unrelated, but this is where this idea of diffusion is kind of coming from. Now, the alternative derivation, I don't really think you need to worry about this. But again, if you've got a burning desire to understand more, we can talk about it after class. So that's just a little note about diffusion there. Okay. So really, the very last piece of the puzzle, and this is what you'll be doing in assignment 3, is to how you're going to apply it to the Black-Scholes PDE. Okay, so we'll go through what's on this slide, and then hopefully you'll have a bit of a picture of how you might attack that, that particular problem. So already I've written up my Black-Scholes equation, my Black-Scholes PDE rather. Okay, so I don't need to worry about writing that up again. I will just insert this condition for completeness. Okay, and we have our terminal condition as well. So these are the pieces of information that we need. Now, bearing in mind that we need to make this, look something like this, then of course we need to change around some variables. But I mean, it's not obviously a million miles away, even at the start. There's, of course, some little differences, but we're really not, you know, a million miles away from where we need to be. So just by some variable substitutions, we'll start off with, I'm going to say that tau is equal to t minus t. We're going to say that z is going to be, let me just underline these as I go. So we've got tau here, here, and z here, and here. Z is going to be log s plus r minus sigma squared over 2 tau. We've got u as some function of both z and tau. Okay, equals e to the r tau times c. And in other words, we can say that u c, and put in our exponential expression. Okay, t minus tau. Because don't forget that this is my stock price. Okay, so it comes from here, right? So this is S, and this is my time coming from here. Right. And it can be shown that this is going to satisfy your PDE up here. Okay, so this is going to satisfy star. So, this is the piece that you will work through here. And remembering here that we've got, obviously, not only substituting into your PDE, but also into your initial condition and terminal condition. So you're going to solve for u using what we saw in the heat equation, and then transform back to obtain the BS formula CBS on 9.12. Okay. So maybe go away, have a think about this. We've got plenty of time to play with in the rest of the semester, so we can always go through these things in more detail. Yep.
Just to clarify, should that be an ES or an EZ?
EZ.
Because it's log of S and we take E of log.
Yeah, but it's because it's C, and we know that C is a function of S and T. We've just rearranged this equation here. Does that make sense? C is some function of S and T. Anyway, again, we can come back to that a bit later if you need to. Okay, so just to note, go away, have a look at this. Next week when we get the assignment question, I can put it up after the guest lecture, and we can talk through it if you need to. So, but just go away and digest what we've done here before you make any dramatic decisions like you can't possibly do it. Okay, so I just want to finish off with a couple of slides. Again, I'm going to be here after class if you want to talk about any of this. Okay, so just some comments, a few generic comments. Basically, if you want to price an option paying something slightly different, such as ST, we'd use exactly the same PDE. We just change the terminal condition. Okay, that's kind of your controlling point. The PDE remains the same. So the terminal condition is what's going to change. This follows from all the replication and the risk-neutral pricing argument. So don't worry about having different PDEs. You won't. The terminal condition will be what controls the different solutions to the PDE. What the replication argument we went through, what that actually proved, is that if the call stock time is a function that actually satisfies the Black-Scholes PDE with terminal data of this nature, then you can have a trading strategy of A, shares, and B, units of the bank account to replicate a claim paying the stock value and self-financing. Okay, that was the whole point of that argument about AT and BT shares and bank accounts. So in order to hedge some claim on the function of stock price, you can use a PDE or risk-neutral pricing to find that option pricing function C, which actually satisfies the Black-Scholes PDE. And then you could calculate DCDS to find the delta hedge, i.e. the coefficient that gives you the number to hold. Okay? So just now we've kind of done the main pieces of the course, and there's also, we're going to do some stuff in Lecture 10 on portfolio optimization. But I just wanted to demonstrate to you how this all fits together with a broad picture. This slide is blank, so I have to draw it for you. So a broad picture. Okay. So basically, the two key factors, dynamics, and in this case we've used Black-Scholes, and the contract features. Okay, so whether you've got European option, American, what have you, blah, blah, blah. So we've got dynamics, in this case being the Black-Scholes, other option. There are other forms of dynamics, though. And so Black-Scholes based on geometric Brownian motion, okay, and whatever the contract type is. Now, from those two key factors, you've got two options. Either you can use replication, which is what we've used, okay? Or you could use a risk-neutral pricing approach, which is in 4091 and 7091. If you use replication, you arrive at your PDE, as we've seen, okay? And if you use risk-neutral pricing, you arrive at your expectation. Martingale expectation. Now, at this point, there's still no price. Okay, when you get here, whether you've replicated or you've used your risk-neutral approach, you still don't actually have a price for an option. If it's very simple, I guess I could move these both into the middle. So simple, very simple contract, so European option, or simple dynamics, for example, Black-Scholes, and you've got your closed form solution. Okay. But more often than not, it's much more complicated than that. And if you have a PDE, to solve it, okay, put this down here as well. To solve it, you'd have to use a numerical method, finite difference or something, which again you'll do in 4091. Okay, and if it's a risk-neutral approach and it's complex, then you'd have to use, say, Monte Carlo. Again, 4091. Then even at this stage, you get the price, But there's still more to do, and this is where your hedging would come in. And then there's a whole other triangle below this where you do all sorts of things with hedging. So, not to depress you, but we're here. And just to give you a picture of why I keep saying some things aren't important and some things are, all we've tried to do is for a very simple set of conditions, simple dynamic, simple contract, we've replicated, we've got a PDE, simple closed form solution. I know it's not really simple, that's like a terribly patronizing thing to say. When you first come across this stuff, it's very complicated, and there are so many elements of maths in it that it can be quite difficult to bring it all together. But just to give you a picture that there's many other ways that you can arrive at the price and even after that do the hedging. So it's just to kind of show you the overall view. But you have got to a way of getting the Black-Scholes PDE, and you also know how to go about approaching getting a solution to that PDE via the heat equation. So yeah, I think that's positive. So yeah. Don't feel too sad. Okay, so I'm going to be here. I can talk through any of those bits we've been through. Also can do some of the mid-semester questions, whatever you like, up to you. But thank you, and see you next week for the guest lecture.